Okay, so we'll go ahead and get started. Hopefully you can see my Canvas screen here. So there were some questions about when you click in your grades, about grades not transferring over from Wiley Plus. So I'm not going to click in there because that will bring up everyone's grades. But basically, the remedy to this is down in your module here, module 2, structural elucidation using spectroscopy. Again, when you click here, that opens the online reading for chapter 14. And then to access the homework, you have to click this link here, or the Orion, click here. If you click into the chapter reading and then you navigate towards like homework or Orion from this link, those grades will not properly transfer over into Canvas. So you have to click this link directly for that homework, this link for that Orion, this link for Orion 15, and like this link for homework 15. So if you're navigating in the book to these things, they don't properly transfer over from Wiley Plus into Canvas. So just make sure you're clicking the respective links for the work that you do. Again, so this is everything you need for Module 2. I just wanted to give you an update on that as to why, if you're not seeing stuff in terms of grades come over from Wiley Plus into Canvas, that's the reason I was told. So here's our slide deck for today. What if we did that for the last module? Kenneth is asking. So basically, I will make sure at some point in the semester that the grade book from Wiley Plus is aligned with the grade book in Canvas. If before then you notice there is definitely an issue, remind me of that, send me an email, and I will manually go in and adjust the grades in Canvas to reflect what's in Wiley Plus. So we'll do a molecule of the lecture, and again, this is the societal relevance of organic chemistry using these LEAP questions, and then we'll get into some more general questions that transition into infrared spectroscopy. So again, this module 2 is all about if we run a reaction and we make a product, how do we know that we have made that product? And so that's what spectroscopy is basically the function of. So we're going to learn, again, mass spec, we talked about that, infrared spectroscopy, and nuclear magnetic resonance spectroscopy. So here's a QR code for naproxen. So why don't you get your phone out and take a picture of that? And that's going to bring up the molecule called naproxen. So here's a slide with naproxen on it. So the therapeutic indication is it is a non-steroidal anti-inflammatory, and these are typically abbreviated NSAIDs. So again, steroids have a specific structure, so these are not steroids. So you're probably familiar with ibuprofen. That's my preferred NSAID of choice. I like to gobble a couple of those a day, make the minor aches go away. And so there's naproxen. That should be what's on your phone right now. So here again, this is the bond line formula for ibuprofen. There's naproxen. Then we have the ball and stick overlay of the space-filling molecule. And so those of you that are going to become physicians or pharmacists, ibuprofen typically looks like this, naproxen like this. And so you look most small molecule pharmaceutical agents have some numbers and letters stamped in them. So these are pretty much universal. So there's actually an iPhone app, probably an Android app as well, that if you have a pill and you take a picture of it, it will basically tell you what that pill is based on the shape, the color, and these numbers. So the mechanism of action of these two things are that it inhibits COX-2. And COX-2, which is this thing shown here, this sort of colored spaghetti rainbow looking thing, is an enzyme. So COX-2 stands for cyclooxygenase type 2. And enzymes are just really big biomolecules that carry out functional group transformations. So in your body, this molecule here, arachidonic acid, is produced. Cyclooxygenase will take up oxygen, arachidonic acid, and basically, if you look at these two alkenes here, it's forming a cyclic ring. So the oxygen is adding across this 1 and 3 position here. So you're forming this, what's called a peroxide, and then you're forming a carbon-carbon bond there. And so these other enzymes then come along and basically do other functional group transformations. So what you can see is this bond cleaves here, and I guess as well what happens in this reaction here is you get a peroxide forming at that sp2 hybridized carbon with migration of the alkene. So many other enzymes take this molecule called PGG2 and turn it into this molecule, which is called a prostaglandin. And so these are the functional group class that are responsible for inflammatory responses. So like if you get stung by a bee and your skin swells, these prostaglandins are what is causing that swelling. So what happens is that these non-steroidal anti-inflammatories inhibit this process from occurring, so you don't get so much swelling. So if you go on to take the biochemistry sequence, you'll learn more about enzymes and mechanisms of action as well. So let's move on to some questions about naproxen. Ian's jumping the gun there. He's got the molecular formula in the chat already. So there's naproxen. Which of the following functional group groups are present in naproxen? I apologize for the stuffiness. I'm having some allergies over the weekend. So go ahead and type a letter in the chat box there for the functional groups present. So again, yeah, the correct answer is D, as in dog. So if we look, we have a benzene ring attached to another benzene ring. We have a carboxylic acid here, and then we have an ether here. So carbon, oxygen, carbon. There's no ester, there's no ketone. So A is incorrect. A thing you want to be cognizant of when you're interpreting structure is that this whole collection of elements here, that's an acid. It's not a ketone and an alcohol. So B is not correct. So again, this is an acid. It's not ketone, alcohol. They're not separate. C is not correct because there's no amine. So again, that's the flavor of how I ask questions. If we were given face-to-face exams, you might see that sort of question. But again, your exams are administered through the test banks and Wiley Plus. So you at least have a different way of seeing questions. So visually inspecting this molecule, how many degrees of unsaturation are present? So Sarah's asking about the benzene rings. So one of these separate is called benzene. So it's actually two benzene rings conjoined, and that has its own name. It's called naphthalene, which is probably where this Na comes from in naproxen. So this name, you might think, how is this collection of letters? What does that mean in terms of this? Because you would, if you didn't know this structure, you would not be able to draw it given that name. So the Na probably comes from naphthalene. So I think the correct answer is 8 for degrees of unsaturation. So there's two rings, right? So there's has to be 6 pi bonds. So we have 1, 2, 3, 4, 5, 6. So those are the pi bonds. Then we have 7, 8, 2 rings, so 8 degrees of unsaturation. So again, the big picture of Module 2 is looking at structures, pulling out this information, and really understanding that, you know, even though this is a line that's it's a black line on a white slide, what does that mean? This is a red O. What really does that mean? So in how do we know that is the structure of naproxen? And again, we're going to use mass spec, IR, and NMR to answer those type of questions. So this one will kick it up a notch in terms of level of difficulty. How many of each type of XH bonds are present in naproxen? So X is going to change, and then hydrogen. So something bonded to hydrogen. How many carbon sp3 hybridized H bonds, sp2 hybridized carbon, sp hybridized carbon, and then OH. So these are all common. There's one. So when you're dealing with multiple choice questions, there's sort of a logic you can take. You cannot eliminate any of the answers based on this because they're all the same, right? So there's the OH bond right there. What about these others? And again, it's asking you for types. How many different types of each of those are there? So let me give you a hint. I'm not talking about the total hydrogen count for each of those. So I'm not talking about the total H count. I'm talking about the types. So how many different sp3 hybridized carbon H types do you see? And the same thing for sp2 and the same thing for sp. So I'm seeing more B as in boy show up in the chat. So that would be the correct answer for what this question is asking. So let's point those out. So sp3 hybridized carbon, there's one here, there's one there, and then there's one there. So that's 3. So just to clarify, the carbons are all sp3 hybridized, but the hydrogens are all in different environments, right? CH3 bonded to oxygen, CH3 bonded to carbon, CH bonded to carbon, sp2 hybridized carbon, sp2 hybridized carbon. So that's what I mean by type. So effectively, there's 3 of those type. So sp2 hybridized H, we have 1, 2, 3, 4, 5, 6. Yes, granted, those are all sp2 hybridized carbon bonded to H. They are all different types. So how do we know that? So however tall you are, I'm 6'4", imagine shrinking yourself down to angstrom level. And now you're standing on this, you're walking along this carbon framework. So you're on this carbon, you're looking out, you see this CH bond. Again, you're standing right there, you see that CH bond, you see this CH bond. Those are not the same type of CH bond, because when you look at their environment around them, this is a carbon bearing no hydrogens, and now this is a carbon with a hydrogen. So those two cannot be equivalent, is sort of what we're getting at. Blakely is asking, what's the difference between the number of hydrogens and the number of bonds with hydrogen? So it's sort of a twofold, like multi-layer concept. So if we're looking at this methyl group here, CH3, and that methyl group there, CH3, each carbon has 3 hydrogens, but they are not the same type of CH3 group. Again, because of their bonding environment. If you're standing here, you look out, you see 3 hydrogens, but then you see immediately an oxygen. If you're standing here, you see 3 hydrogens, but then you immediately see a carbon. So those groups are different. They're not the same type. And there are no sp hybridized carbon in this molecule. So maybe in the chat box, what functional groups have sp hybridized carbon? There's 2, probably 3 that you're aware of. So yeah, alkyne is one of them. What's another one? Alkyne is a carbon-carbon triple bond. So Aiden says compound alkenes. Max says 2 double bonds such as CO2. Yeah, that's another one. Carbon dioxide. So Aiden, I think if I'm inferring correctly, you're probably thinking of like what Max said with carbon dioxide, but instead of oxygens, you have carbons. So those are called allenes. Let me write that in the chat. A-L-L-E-N-E, allene. So allene, carbon dioxide, yes, those are also functional groups that have sp hybridized carbon. So there's one more that's pretty common, has sp hybridized carbon in it. So it would be at an oxidation state of 3, meaning that it has 3 bonds to a heteroatom, if that jogs your memory. So if the heteroatom was nitrogen, carbon bonded 3 times to nitrogen. So that's called a nitrile or a cyanide. So let's go on. We'll do one more question with naproxen here. So of the types of pi bonds in naproxen, which one has the larger dipole moment? So yeah, the correct answer is B as in boy, so the CO pi bond. So what is the reason for that? Why is the carbonyl group, as it's called, the CO pi bond, why does that have the larger dipole moment? So yeah, Taka, Hana, Cardi, Jalen, it's due to the electronegativity difference between oxygen and carbon. So we could say that a carbon-carbon pi bond, if we're sort of ignoring substituents, things bonded to it, that's non-polar. A CO pi bond is polar due to the electronegativity difference between oxygen and carbon. And that concept of the size of the dipole moment is what gives rise to infrared spectroscopy. And so that's what we're going to cover in a practical sense today, and I'll have some screencasts posted in the next day or two. I had to go through some revisions of my slide deck, so I'm updating them a little bit. So before we get into IR right now, let me ask you 3 more questions about functional groups. Because as this title says, we really want to understand the different ways of communicating functional group information. So which of the following correctly matches the functional group name? So up in the first row here, these are the names: primary amide, alkyl chloride, acid chloride, with the general condensed formula. So in organic chemistry, we use R as like your variable, like X would be in algebra. So R can be anything. So which of these answers has a primary amide, an alkyl chloride, and an acid chloride in the condensed formula? So if you think about another aspect of what this question is asking you, it's sort of like how you would write simply only in letters what could be conveyed in a Lewis structure or a bond line formula. So you're taking those, you're not seeing really the bonding pattern the way that things are presented in a condensed formula. The correct answer is D. So a primary amide, we have the carbonyl bonded to NH2, and again, R is pretty much anything. Alkyl chloride, we have RCl. In the acid chloride, we have the carbonyl directly bonded to a chlorine. And so again, throughout this semester, with our student learning outcomes, we're layering this information. So again, the next layer that we're putting on top of this is this name here, this collection of letters to form words: acid chloride, this condensed formula RCOCl. The next layer we're putting on top of that is experimental data. How can we look at an infrared spectrum and know that an acid chloride is present? So here's another one: carboxylic acid, alcohol, aldehyde. So yeah, C is probably the best choice. Again, given the nature of this class, we're COVID, things are online, yada, yada, yada. This would be how I ask questions, how you would see them on exams. And typically with multiple choice questions, there's a strategy you can take where, you're sort of eliminating, if we're just considering carboxylic acids, that's A or C. So immediately we can get rid of B and D. We don't even have to consider alcohols or aldehydes for that row. So we're choosing between A and C. So the next one, alcohol. Alcohols have to have a hydroxyl group, OH. So we can see that C is going to be the correct answer because this is the formula for an aldehyde, which we see here. RCHO. So notice the difference between alcohol and aldehyde. Again, in an aldehyde, if you draw this out in the Lewis structure or the bond line, this H is not bonded to that O. So it's implicit that you understand that. So one more. Primary amine, ether, and ketone. So primary amine, ether, ketone. So Carly asked about Wiley Plus. We actually switched to Wiley Plus. We switched to it back in spring. Prior to that, we were using sapling. The reason that we switched is because the Wiley Plus is directly connected to the course textbook, whereas sapling was not. It really did not have anything to do with COVID so much. So yeah, the correct answer for this one is A. An amine has a nitrogen. This happens to be a primary amine because there's one bond to carbon and two hydrogens remaining. Ether is carbon, oxygen, carbon, and ketone is carbon, carbonyl, carbon. So A is the best choice for this one. So I want to basically transition now into infrared spectroscopy. And again, this is going to be a very practical introduction to it. I'll have the more formal lecture screencast posted today or tomorrow. Again, I'm creating new slides for each functional group to show you not only the static spectrum, but also a short movie that shows you the actual bonds involved. So here we go, infrared spectroscopy. This is the experimental determination of functional groups in a molecule. So we're gonna for these next couple of slides, we're gonna look at ibuprofen because that's the one I could find an actual IR for. So this is what an infrared spectrum looks like. So again, IR spectroscopy is an instrumental technique that's used to determine functional groups in the molecule. So you can look at this, you can say these are carboxylic acid, there's a benzene ring, we have a couple different types of sp3 hybridized carbon H in here. So IR can tell you sort of qualitatively what functional groups are there. The physical phenomenon that is happening is perturbation of a bond dipole moment by IR light. So in the lecture screencast, I'll briefly go over the electromagnetic spectrum. So again, a spectrum is not a continuum. A spectrum has defined like starting and end points. So IR light is a part of that spectrum. what you and I see now, that's visible light, right? So IR light, our eyeballs are not configured to see that. So here's ibuprofen. We have an acid functional group, and that's really the primary functional group that IR will indicate to us. So this is an IR spectrum. The x-axis is in this unit called wave numbers, and that's abbreviated reciprocal centimeters. Again, I'll explain how that is derived in the screencast. But for now, what do you need to know? The x-axis runs from 4,000 wave numbers to 400 wave numbers. The y-axis is percent transmittance. So maybe in the chat you can say yes or no. Are you familiar with Beer's law? So this has nothing to do with how many beers you can drink. Beer's law. Did you do an experiment in Gen Chem lab on Beer's law? Getting some yeses, some nos. So the way you can sort of think about interpreting this graph is it's similar to Beer's law. It's concentration and absorbance. So on the y-axis is percent transmittance. Now imagine basically the way this instrument is set up. You have your sample ibuprofen in a vial, and then you're shining an IR laser through that vial. On the other side of the laser is a detector. It's detecting the light. If there is 100% transmittance of that light through the sample, nothing is being absorbed, right? Is that clear? So at the top of this axis is 100% transmittance, which means there's zero absorbance. So let's just say you're reading this, in Western culture, we read from left to right. That's how you read sentences, right? So let's just, our eyeball is scanning this baseline, the baseline of the spectrum here, from 4,000 to 400. So we're starting here, it's about 100, right? That means as this laser intensity is going through the sample is not absorbing anything. 100% of the light is going through the detector. But notice as we start to get around 3,600, it's starting to absorb. So again, transmittance, absorbance, they're inversely related, right? So as we decrease in wave numbers, the percent transmittance here is decreasing. So at around, say what, 2950 or so, this wave number here, we go up, boom, we're at 20% transmittance. That means that at that frequency or energy of light coming in, it's being absorbed, right? And so the detector is not seeing as much light come out of that sample. So what does that mean? That means that one of these functional groups present in that molecule is absorbing that light. And so if you look at the range from 4,000 to 400, that span of 3,600 wave numbers, across that span, where you see these peaks, where something is absorbed, I know that sounds weird because it's going down, we're calling it a peak, a signal, whatever. Where it occurs is indicative of what type of functional group is present. So we have this really broad signal here. Boom. Then it's, as we scan this way, it's going back up. So we're at 100% transmittance again. Our eyeball is coming down. We see another signal. So this is absorption. Transmittance is decreasing. This is another peak here. So again, our baseline coming down, going back up, coming down. So this is a signal. So 16, 1650, 17, we're about 1725, we're seeing this signal. So then we get to this region here, we're going back up in around 1500. Look at all these peaks here. Man, that's crazy. You drive yourself nuts trying to figure out what all those peaks belong to. So fortunately for us, anything from 1500 below to 400, you just ignore it. So let's go to this slide here. And this slide shows you the 4 regions that you have to be concerned with and what functional groups occur in those regions. So IR spectra are good for determining what functional groups are present. So by present, that means you see the peak. It's going from the 100% transmittance, absorbing down, and then back up. So we're calling that a peak or a signal. So it can tell you what groups are there. And if you don't see that group, what group is not in that molecule. So both of those things are useful. Since all molecules have CH stretching, basically we're going to look to region 3 first for strong absorption. Then we look to region 2 for sharp absorptions indicative of a triple bond. So let me go through these regions. Region 1 is about 4,000 to 2,750. I've colored that in blue. That is the XH stretching. So your carbon, hydrogen, oxygen, hydrogen, nitrogen, hydrogen stretching. They'll all occur in this region. Region 2 is the triple bond region. So alkyne, nitrile, cyano, or this N3 group that's called azide. So only those 3 occur in region 2, which is 2,500 to 2,000. Region 3 is your double bond region, carbonyl, the CN pi bond, that's called an imine, and then your CC pi bond, your alkenes. Those occur from about 1,600 to 1,800. And then this region 4, which is called the fingerprint region, that gets way too complicated to interpret. So we for most part, for this class, we just ignore it. If you go on to become a professional chemist and you study IR, you can get into that. But really, we're concerned with regions 1, 2, and 3. And so according to this short algorithm here, because all molecules have CH stretching, we know that it's everything we look at is going to have a peak there. So really, we want to go to region 3 first to see if there's a peak. That can tell us if there's a CO pi bond, CN, or CC. Really, for the most part, it's CO, because those are the strongest, right? Because we said, based on the difference in electronegativity, those will have really strong absorptions or peaks. Then you can go to region 2 to see if there's alkyne, nitrile, or azide. So I'm going to throw the ibuprofen spectrum back up, where I've identified these stretchings now, or these peaks, according to the different regions. So look at region 1. This is really broad, right? This whole thing is sort of in region 1. We have OH stretching. That's what leads to this broadness. All the different CH stretching. You have this methyl group, this methine, these benzene ring, CH stretchings, methylene, methine, methyl. All those different types of CH bonds occur in this region. So it's really hard to ferret out that it's specifically those types. So what this region 1 tells us is that, okay, there's OH, because we see very broad peak shape. And again, I will go through all the different functional groups in the separate lecture screencast so that you can pick out the diagnostic peaks. Region 2 has nothing. Even though this peak is coming up into region 2, there's no really strong absorption occurring. So if you look, there's no triple bonds, right? We don't see any, so therefore that's the absence, right? This piece of data does not show a peak there, and we know that based on looking at the structure. Region 3, we see a really strong peak. That's the carbonyl of the acid. So carbonyls occur between 16 and 1800. So we can say region 3, we can assign that really strong peak to this CO pi bond. And then anything below 1500 is called the fingerprint. So you can see, you look at your own fingerprints, they're all unique. Every molecule has a unique fingerprint region, so we ignore it because it's really hard to interpret. So any questions on this before we actually get to a piece of data and I start asking you some questions? And again, maybe I can bring up my other slide deck to show you what I'm working on. And again, because we're online, I need to basically put this in a little bit more context so that as you go through the video, this is sort of what I'm working on in terms of the slide deck. Each functional group will have what I'm calling sort of the static IR. Basically the diagnostic peaks, and then there's a little movie. So can you all see that movie that's showing right now? So really what the movie is showing you is what is happening when you observe these peaks. See this peak right here? Those are CH stretchings. So the actual static spectrum doesn't give you so much of an idea that this is actually what's going on. So you see that OH bond? That's this really broad peak there. And so I'm slowly getting these all together for the different functional groups. And this will be its own screencast. I just haven't had time to finish it yet because there's some other functional groups I have to put in here yet. And there'll be a more in-depth explanation of the electromagnetic spectrum, etc. So a couple questions in the chat. Resonance of the double bonds in the benzene ring. That's really sort of a very specific question for IR. You can pull that detail out of an IR spectrum, but it really takes a trained eye to do that. Yeah, so Mac is asking about compounds of the bonds get heavier or lighter from left to right. So yeah, basically, if you look at this spectrum, you have these are bonds, 2 hydrogens, so you have light atoms sort of to the left of the spectrum, and then as you move towards lower wave number, towards 400, that's when you get the heavier atoms in there. So for example, if you had like a carbon chlorine or carbon bromine bond, you would see that peak in the fingerprint region. So look how messy this fingerprint is. So that's not good for picking out those type of bonds. That's why we would go back to mass spec and look at the parent ion and mass spec to figure out if there was a halogen involved. So that's why you have to synthesize in a way, you have to put all this data together, make sure that it meshes, and when you propose a structure, you're not like invalidating your claim. So here's a problem. I call these problems putting it all together. So determination of possible isomers from mass spec data, IR data at this point. So here's the problem. Given a mass of m to z equals 72, so that's the parent from a mass spectrometer. A strong absorption shown here at 1730. And I'm telling you, so this is an IR spectrum. I'm telling you that belongs to a carbon-oxygen pi bond, a carbonyl group. Determine the molecular formula and propose possible structures that match this piece of data with this piece of data. And then of the claims you are making, how do you differentiate the isomers by carbon-hydrogen uniqueness? What are the different types of carbon hybridization? And then what are the ratios of hydrogen sets? So Mac in the chat is asking about carbon-chlorine single bond, be to the right of a carbon-carbon single bond. Yeah, I believe it would be, and I'll explain that stuff in the lecture screencasts. Is basically as you move to the right, the atoms get heavier. So again, we're going to talk about the spring model for a bond. And so as you get heavier atoms, the stretching frequencies move to lower wave numbers. So for now, I'm going to flip this around. So if you pin the camera there, it should be on the dock cam. So let's write down some of this data we're given. So mass spec, parent m to z is equal to 72. IR, it's telling you it has a carbonyl group at 1730 wave numbers. So what is the molecular formula? So Ian and James are saying C4H8O. Tenley has also corroborated that piece of, or that claim. So again, we're calling this module structure elucidation using spectroscopy. And again, my goal or my sort of mission in teaching you guys is to how do you think and solve problems. So let's see how did they come up with C4H8O. So we said in the IR that there's a carbonyl group. The carbonyl group is telling you there's an oxygen, right? Carbonyl has one oxygen. What is the atomic mass of oxygen? (16). So at this point, I'm pretty much making it I'm just telling you there's a single oxygen in the molecule. So the parent was 72. So this is all C, H, and O. We said there's a single oxygen, so what does that get us? 72 minus 1 oxygen. 72 minus 16, what is that, 56? So look, all CH and O were in 72. We subtracted out that oxygen. The 56 contains all the carbons and hydrogens. So how do we do max number of carbon? (56) divided by the atomic mass of carbon is 12. That's really just going to get us 4. 12 times 4 is equal to 48. So the max number of H is equal to 56 minus 48. And that gets us 8. So 1, 4, 8. C4H8O. So how many degrees of unsaturation are present in that molecular formula? So yeah, if we have N equals 4, and we do CnH2n plus 2, C4H10, this is fully saturated. Our molecular formula, oxygen, again, doesn't contribute. So we come up with 1, but look back up here, remember from the IR? The IR is telling you that there's a carbonyl group, right? So how many degrees of unsaturation does a carbonyl group have? This has 1 degree of unsaturation. And that's what we just calculated, right? So that 1 degree of unsaturation is the carbonyl group. So when you're proposing structures, we can sort of do something like this, right? C4H8O. We know that from our calculations has 1 degree of unsaturation. We already know that CO, the carbonyl fragment, has to be in there from IR. So that has 1 degree of unsaturation, right? So if we take those elements out, we have C3H8. Those have 0 degrees of unsaturation remaining. So you have to use this fragment with that to come up with possible structures. So you can either write the name in the chat box of those structures, or show your structures through your camera. Then we can write them down and consider what could be the possible isomers for that molecular formula. So Alexis is asking about this manipulation here. So C4H10 is for 4 carbons, should have 10 hydrogens when it's fully saturated. C4H8 is what we came up with from what we found. Remember, oxygen does nothing to this hydrogen count. So we have C4H8. H10 minus H8 is H2. And this H2 is what is defined as a degree of unsaturation. So James, it looks like you have 2 of them. I think we can get another one, another possible. So I'll give you some time before I write down the possibilities. So maybe we can we know that there has to be a CO pi bond in our claims. So C3H8, that has no degrees of unsaturation. So what if I just start by drawing a linear chain? 1, 2, 3 carbons, right? And so what if I put this last carbonyl group here? So now I have 1, 2, 3, 4. Let me just draw this H in. C4, 1, 2, 3, 4, 5, 6, 7, H8O. What functional group is this? So this is one possibility.
All right, this is we gotta have one. We gotta have like a
So Ian says it's an aldehyde. So notice when I did that 4 carbon chain, I put the carbonyl group at the end. What if I put it here? C4H8O. What functional group is this? It's not an ether. It's not an ester. Remember, an ester has 2 oxygens. Yeah, Garrett has it right. This is a ketone. So there's actually one more isomer that we can draw, which I'm just going to put in terms of, I'm going to put it down because we're sort of running out of time. So there's a 3 carbon chain. There's a carbonyl. This is also C4H8O, and this is an aldehyde. So those are 3 possibilities that all contain a carbonyl group. So what the last question was asking you, how do you differentiate them by carbon-hydrogen uniqueness? How many different types of carbon hybridization are there, and what are the ratio of the hydrogen sets? So because we are out of time, what I want to just close with is show you this slide here. And I've given you now, so Katie's asking, why did I draw these hydrogens out for the aldehyde? That's typically the convention. For the aldehyde, you do show them. So I've given you a transition into NMR spectroscopy, and I know we're sort of at 12, but let me just get a minute to finish here. The top spectrum is proton NMR. The bottom spectrum is carbon NMR. So specifically look at proton decoupled. This thing at solvent you ignore. And what that final prompt was asking you, so the unique number of carbons for each of these, unique sets of hydrogen, and their ratios. So what we'll do on Friday is we'll pick up how you answer those prompts and what that means in looking at this given data. And then we can determine from this data which one of these isomers that is. So look for a couple screencasts to be posted in Canvas on Mass Spec and IR over the next day or two. And we'll continue on with this spectroscopy problem solving on Friday. Again, shoot me a question if you have any, or shoot me an email if you have any questions, and try to get to your homeworks 14 and 15. Other than that, we'll see you Friday.